Hello friends, welcome to this lecture. And if you recall, in previous lecture we have discussed one example stating that the behavior of the nonlinear system is may be very different from the behavior of the linear system. In fact, we have pointed out that in nonlinear system it may happen that the orbit of a closed curve, orbit of a solution which is a closed curve may spirally approached by the solutions, the orbit of the other solutions, and that orbit is important in the sense that it will correspond to a orbit of a periodic solution. And we have discussed the Poincare-Bendixson theorem to find out the existence of the orbit which is corresponding to periodic solution. So, in previous lecture we have discussed the Poincare-Bendixson theorems, which will give you the existence of periodic non-trivial periodic solution. But we have also noted down that it gives just the existence, it will not discuss which curve is corresponding to the curve of periodic solution. So, in this lecture we will try to focus on the curve which will the orbit which will correspond to the orbit of periodic solution. So, here we will start this lecture by defining the limit cycle, and with the help of limit cycle we try to find out that this will correspond to the orbit of the periodic solution. Okay. So, let us decide the define the limit cycle. Okay. Now, let us take this following definition. A closed curve C is called a limit cycle of dx by dt equal to fxy, dy by dt equal to gxy if orbits of this spirals into it as t tending to infinity. So, it means that the orbit corresponding to non periodic solution is called as limit cycle. So, it means that a limit cycle is called stable limit cycle if all the orbits of 28 sufficiently close to this at any given time t must spiral into it, otherwise it is called an unstable limit cycle. So, it means that first of all, what is limit cycle? Limit cycle is the orbit, closed orbit onto which your solutions are spiraling onto which. Okay. So, limit cycle is this. Now, limit cycle may be of different type, stable limit cycle and unstable limit cycle. When it is called a stable limit cycle, if we take a orbit which is at some time it is near to that orbit must be spiral onto this orbit, closed orbit, then your limit cycle is known as stable limit cycle, otherwise it is called an unstable limit cycle. Now, next example is find all limit cycle of the system x dash equal to x minus x cube minus xy square and y dash equal to y minus y cube minus y of x square. So, here we can find out like as I pointed out that try to find out d by dt of x square plus y square upon 2, this is nothing but r of r dash. So, if you look at this is nothing but r square into 1 minus r square. So, it means that it is r square 1 minus r square. So, we can say that r dash is equal to r into 1 minus r square, right. Now, here we want to find out the limit cycle. So, limit cycle is basically if you look at the this will critical point is r equal to 0 and r equal to 1 here, r equal to minus 1 is so it means that here we are two critical point of this 0 and this one. Now, I am saying that this r equal to 1 is the limit cycle, right, and we can check that it is a stable limit cycle. So, we can say that if we take, as we pointed out here, if we take any point here, then it will say move away and it will try to reach on this curve r equal to 1, and if we take any solution outside, then it, dr by dt will be decreasing and it will try to come on to this. So, we simply say that here r equal to 1 is a closed orbit, right. Yeah. So, we simply say that there are two orbit r equal to 0 and r equal to in fact it is a critical point of this system, r dash equal to r into 1 minus 1. So, r equal to 1 is one of the orbit, closed orbit. Now, we want to show that this r equal to 1 orbit is nothing but a limit cycle, and that we can show that if we take any solution inside your region R, let me look at here, you can use this thing. So, here we have, and now if we take solution which is here, then it will try to move away and try to be on the limit cycle. Once it is there, it will always remain there, and similarly if we look at some other solution say which is outside this, then it will always try to be on the say r equal to 1, and as soon as it is on r equal to 1, it will always be on the orbit r equal to 1 here. So, now which it means that your r equal to 1 is your orbit, and all the other solutions are spiraling onto r equal to 1, and hence by definition r equal to 1 is a limit cycle. And now if we want to look at the stable and unstable limit cycle, then we can simply say that if you look at this solution somewhere here, and it is near to r equal to 1, then we can see that it is always tending towards r equal to 1. And similarly, if we take any other solution which is outside unit cycle, it will also coming to r equal to 1. So, it means that in this case r equal to 1 is a stable limit cycle, right. So, it means that it is a limit cycle and it is a stable limit cycle. Similarly, if you look at r equal to 0, it is also a trivial limit cycle, and we can check that any solution which is near to origin, it is going out of the means going away from the origin. So, we can say that 0 is a trivial limit cycle which is unstable limit cycle. Now, next example is a generalization of the previous example. Show that the system x dash equal to y plus x f r upon r, y dash equal to minus x plus f y f r upon r, where r is equal to x square plus y square under root, has limit cycle corresponding to the zeros of f of r, and what is the direction of motion of these curves, that we wanted to find out. So, if you look at how we look at, so x dash plus y dash, if you want to find out, then it is x y plus x square f of r upon r plus minus y of x plus y square f of r upon r, and if you look at, this is nothing but x square plus y square f of r upon r. So, it is r into f of r. So, x dash plus y dash is equal to r f of r. Now, this I can write as 1 by 2 of d by dt of r square, right. So, now I can rewrite this as r dash equal to r f of r. So, it is r dash equal to f of r. Now, zeros of f of r will give you the equilibrium solutions or fixed or critical points of r dash, right, this r dash equal to f of r. So, it means that zeros of this will give you say closed curves, right, and now we can check that these closed curves are nothing but limit cycles, and the direction will be given by this thing. So, it means that suppose we have a orbit like this. Now, we can check that at this point your x is positive and y dash is y is equal to 0 here and x is positive. So, the direction will give you by this, that y dash equal to minus x plus y is equal to 0. So, that part is gone. So, y dash equal to minus of x. So, here x is positive. So, y dash is negative. So, it means that y has a tendency to decrease. So, it means that the direction is clockwise, right. So, it means that the zeros of f of r gives you a closed curves which we can show that it is a limit cycle, and the direction of your movement on the orbits are downwards, means clockwise. So, that is what it is given here. Okay, here now we say that suppose we have not proven that limit cycles, these are limit cycle. So, for that let us say that f of r has two roots, say r naught and r 1. So, it means that it has r naught and r 1, which is r 1 is bigger than r naught. So, we can use wavy curve method and we can write this thing, right, and with the help of this you can check that which one is a stable limit cycle and which one is the unstable limit cycle here. So, we have seen here that it is r dash equal to f of r here, and we can also check the direction of these orbits here. So, the zeros of f of r will give you the critical point of r dash. It means that r equal to say r equal to say r 1, r naught, r equal to r 1, r equal to r 2. If these are zeros, r 1 where r naught, r 1, r 2 are zeros of f of r, then this will give you the critical point of r dash. It means that these will give you the orbits of the solutions of this nonlinear system, and we can see that the moment of your solution on these orbits are given as clockwise, that we have pointed out from this. Now, our claim is that these orbit which are the zeros of f of r are basically the limit cycles and correspond to the periodic solutions. So, solution corresponding to the periodic solutions. So, now let us say that these are orbits r naught, r 1 and r 2 are your limit cycles. So, for that let us look at here that f of r equal to 0 for r equal to r naught, r 1 and r 2. So, let us arrange in an increasing order. So, r naught is bigger, less than r 1 and it is something like that. So, r naught is certainly positive here, in fact it is greater than r equal to 0 here. So, let us have these things. So, r naught, r 1 and r 2. So, by wavy curve method I can write it f of r equal to r minus r naught, r minus r 1 into r minus r 2, and we can have wavy curve method like this. It is minus plus minus plus. It means what? That if r is bigger than r 2, then what is the sign of f of r? So, if r is bigger than r 2, then this will be positive, r is bigger than r 2, and this will again be positive, and all are positive. So, f of r is positive here. So, if f of r is equal to r minus r naught, r minus r 1, r minus r 2, then we can use wavy curve method to find out the sign of f of r as follows. So, if it is plus when r 2 is r is bigger than r 2, and it is minus if r is lying between r 1 and r 2, and it is plus again when r naught is lying between r is lying between r naught and r 1, and negative r is less than r naught. That you can verify. Let us say that take r as somewhere between r naught and r 1 here, then this r minus r 1 is here it is negative, right. R minus r 1 is negative here, and r minus r 2 is also negative. So, it is negative negative, and r minus r naught is positive. So, it will be positive here. So, f of r will be positive here. Now, with the help of this we try to check that these are limit cycle. So, this is corresponding to r naught, this is corresponding to r 1, this is corresponding to r 2 here. Now, we want to check whether this will be limit cycle or not. So, first if you look at this r equal to r 2 here. So, it means that it is one of the orbit, first of all it is clear. Now, if I take any point r here, right. So, it means that let us start with a solution which is somewhere here. So, it is starting is here somewhere. Then if you look at dr by dt will be what? Dr by dt equal to f of r here, that we have pointed out here, that dr by dt equal to f of r here. Now, as r is bigger than r 2, then r is bigger than r 2 means this is positive. So, it means that f of r for r bigger than r 2 is positive. So, it means that dr by dt is say positive. So, it means that it is keep on increasing. So, it means that any solution which start from this, it will try to move away from r equal to r2. So, it means it is moving like this, right. So, it means that it is moving away from r equal to r2. Now, if I look at any solution which start in this region bigger than r1 and less than r2, and here it means that r is lying between r1 and r2, it means r is lying somewhere here. Then your dr by dt equal to f of r, and for that r your dr by dt will be negative, because f of r will be negative if r is lying between r1 and r2. So, it means that for that your dr by dt is decreasing. So, it means that it has a tendency to decrease the radius as t tending to infinity. So, it means that if it start from this, it will try to decrease the radius. So, it means that the r equal to r2, any solution which is near to r equal to r2 has a tendency that as t tending to infinity, your solution will move away from r equal to r2, or I can say that as t tending to minus infinity, all the solutions which are near to r equal to r2 has a tendency to spiral on r equal to r2. Please mind here that t is equal to minus infinity. So, it means that this r equal to r2, which is a orbit of the given nonlinear system, has a tendency that all the solution which is lying starting near the orbit r equal to r2 has a tendency that as t tending to minus infinity, all the solutions are approaching or r equal to r2. So, it means that r equal to r2 is by definition it is a limit cycle and unstable limit cycle, right. So, we have shown that r equal to r2, all the solution which start near r equal to r2 are approaching r equal to r2 as t tending to minus infinity. So, r equal to r2 is a limit cycle which is unstable. Now, look at r equal to r1 here. So, for r equal to r1, we can look at this, that if your solution start between which is bigger than r1, then we have seen that it is trying towards r equal to r1 here. Now, if I look at the solution which starting somewhere between r0 and r1, then solution for r lying between r0 and r1, your f of r is positive. So, it means that dr by dt is equal to f of r, where if r is lying between r0 and r1, f of r is positive, it means that radius is keep on increasing. So, it means that any solution which start in this annulus region will have a tendency that it will moving towards r equal to r1 here. So, it means that if I take this solution which is lying between r1 and r2, then it will converge to the solution at r equal to r1, and if we take any solution inner to r1, then it is moving towards r1 itself. So, it means that corresponding to r equal to r1, if we take any solution in the neighborhood of r equal to r1, then as t tending to plus infinity, all the solution will try to merge on the orbit r equal to r1. So, it means that by definition the r equal to r1 is a closed orbit onto which all other solution which are nearby to r equal to r1 will merge, try to merge on r equal to r1 as t tending to infinity. So, it means that by definition r equal to r1 is a limit cycle which is a stable limit cycle, and this will correspond to a solution which is periodic in nature. So, r equal to r1 is a orbit of a periodic solution. Similarly, if you look at r naught here, we have already seen that if we take any solution between r naught and r1, it is moving towards r1, not r naught. So, if we take any solution here which is between 0 and r naught, then here we have already seen that f of r is negative. So, it means that dr by dt equal to f of r, and if r is less than r naught, then f r are negative. So, it means that it is trying to reduce the distance from the origin. So, it means that here solution which is inner to your r naught will try away from R naught, try to be away from R equal to R naught. So, it means that corresponding to R equal to R naught, if we take any other solution which is in the neighborhood of R equal to R naught, will try to merge to R equal to R naught as t tending to minus infinity. So, in this case R equal to R naught correspond to a closed orbit, means it is corresponding to a periodic solution, and all other solutions are merging to R equal to R naught as t tending to minus infinity. So, by definition this R equal to R naught is also a limit cycle, which is an unstable limit cycle. So, what we have shown here, that if f of r equal to 0 for r equal to r naught, r1 and r2, then the orbit corresponding to r naught, r1 and r2 are limit cycles, which may be stable or unstable depending on the situation here, right. So, it means that the zeros of f of r are limit cycle, and it will correspond, these limit cycles are correspond to the solution which are periodic in nature. So, that is what we have concluded this, that in this problem x dash equal to y plus x f r by r, y dash equal to minus x plus y f r upon r has limit cycle corresponding to the zeros f of r, and the direction of motion on these curves are clockwise, that we have already pointed out. So, this conclude the example 4 here. Now, next is the Bendixson non-existence theorem. If you look at here in previous example, what we have shown here, we have exactly shown here the existence of say limit cycle. Now, in many of the problem it may not be so nice here. So, here we have one negative theorem in the sense that this will negate the existence of limit cycle, because for limit cycle we must have two things. First thing is that we must have a closed curve, and the second thing is that all the other solution which in lying near to your closed curve must spiral onto the closed curve as t tending to plus infinity or minus infinity. Then we say that the closed curve is a limit cycle. Unstable and unstable will depend on the condition that your curves are approaching to the closed curve as t tending to plus infinity or minus infinity, and many a times it may also happen that one side it is approaching and other side it is say moving away. So, it means that that kind of thing we can say that it is half stable or half unstable, but it is not called as stable or unstable. Okay. So, that kind of situation may also happen. So, now let us look at this important theorem which negate the possibility of limit cycle. So, basically it will negate the possibility of closed orbit. So, it says that let D be a domain in xy plane and consider the autonomous system x dash equal to f x y and y dash equal to g x y, where f and g have continuous first order partial derivative in that domain. Then the system 29 has no periodic solution in the domain D if this f x plus g y has the same sign. It means that it is not changing the sign, then it will not have any periodic solution in that particular domain D. It means that if there is no periodic solution, then there is no possibility of limit cycle. Is it okay? So, basically it is a negation of the Poincare-Bendixson theorem. Negation in the sense that it is giving you that there exists no limit cycle of the linear system, not negation of the Poincare-Bendixson theorem. Okay. So, let us have a proof of this. So, let us say that let C be a closed curve in D and R be the region bounded by C. So, this is important, that C be a closed curve in D. And now, applying Green's theorem of the plane, we can have integral of line integral of f x y dy minus g x y dx equal to double integral over R f x plus g y d of s here, where s is the surface integral. So, basically it is a famous result say connecting the surface integral and line integral. and here the line integral is taken in the positive sense, anti-clockwise. Now assume that C is a closed path of the given system, and let x equal to x star and y equal to y star be an arbitrary solution defining C parametrically. So it means that let us say that x star and y star define this closed curve, and let us say that this C does not contain any limit point, critical point. So it means that this C correspond to a periodic solution given as x equal to x star and y equal to y star. Now we say that if f(x) plus gy will not change sign in that domain D, then this is not possible. So let T denote the period of this solution, and then along C dx star dt is equal to f x star y star, and dy star dy by dt of y star is equal to gx star y star t, and we can write down this line integral c f x y dy minus gx y dy dx as we simply write dt here, and this is dt here and t here. So we convert this line, parameterize this c in terms of t, and we can write this line integral as 0 to t f x star t y star t dy star by dt minus gx star t y star t dx star by dt here, right. Now if you look at what is this dy star dt, it is g here. So it is nothing but f into g minus g into f. So this has to be equal to 0 here. So it means that the right hand side which is given by this has to be 0. So double integral f x plus gy ds equal to 0. So this surface integral will be 0 provided that the integrand must change its sign, but if f x plus gy is not change their sign, then this integral cannot be equal to 0. So it means that if f x plus gy will keep the same sign, then your then this may not happen. So it means that this is true only when we are assuming that C is a closed curve. So it means that if C is closed curve and f x plus gy is having the same sign, then this cannot be true, right. So it means that the contradiction we are getting is only because we are assuming that C is a closed curve say bounding the domain R here, right. So because if C is a closed curve, then it has to be 0, but f x plus gy is having same sign, then it cannot be 0. So it means that the assumption that C is a closed curve is not true. So it means that C cannot be closed curve, and hence this C is not correspond to a the periodic solution. So C is not a orbit of a periodic solution. So it means that there exists no closed path in domain D here. So it means that if f x plus gy will have the same sign, then D cannot have any closed curve, right, and hence no periodic solution, because if it has a closed curve which will not contain any critical point, then it must correspond to a periodic solution. So let us have one example based on this. So that the system of differential equation dx by dt equal to x plus y square plus x cube and dy by dt equal to minus x plus yx square has no non-trivial periodic solution. So as we have pointed out, this is nothing but f of x comma y, and it is having g of x comma y. So look at f of x is 1 plus 3x square. When we write f of x, we are keeping y as a say constant. So similarly you can find out g of y is 1 plus x square, and if you look at f x plus gy, it is nothing but 2 plus 4x square, and since x this will always remain positive. So it means that and this is positive for all x y in R2. So it means that for in R2 it will not have any closed curve. So it means that any of the solution will not form any closed orbit, and hence this system will not have any non-trivial periodic solution here. Now let us consider one more example. So if you look at this is always true for all values of x y. It means that this will not have any periodic solution in an entire R2. Now, let us look at the next example. Show that the system of differential equation dx by dt equal to x minus xy square plus y cube and dy by dt equal to x cube plus 3y minus yx square has no non-trivial periodic solution which lie inside the circle x square plus y square equal to 4. So, as we have pointed out, this is your f of x comma y and this is your g x comma y here. So, we can find out f of x, which is nothing but 1 minus y square, and g of y is equal to 3 minus x square, and we can see that f of x plus g of y is equal to 4 minus x square minus y square. So, it means that if x square plus y square is less than 4, then it is positive, then f of x plus g of y is positive. It will not change any sign here. So, it means that in that domain this x square plus y square equal to 4, in that region we do not have any closed orbit here. It means that in this domain x square plus y square less than or equal to 4, we do not have any closed orbit, and hence we do not have any non-trivial periodic solution which lie inside this circle. So, with this we conclude our lecture here. So, what we have shown here that if we do not have any closed orbit, then we do not have say limit cycle, and we do not have any non-trivial periodic solution. So, for existence of periodic solution and hence for limit cycle, we must have a closed orbit. So, Bendixson non-existence theorems will simply gives you that if fx plus gy remains the same sign in a given domain, then in that domain we do not have any closed curve, and hence we do not have any possibility of having closed orbit, and hence we do not have non-trivial periodic solution, as well as there exists no possibility of limit cycle. So, with this we conclude, and we will continue our study in next lecture. Thank you very much for listening us. Thank you.